So, this VBG is (1.15 volt to 1.3 volt). That is what you get, which means how much VDD you require to generate this band gap? Obviously more than 1.3. So, VDD required is more than 1.3 volt, approximately 1.5 volt or so. That is the minimum VDD you require. Okay. So, you cannot operate this below 1.5 volt, this band gap. And these days you have devices which are like 1.2 volt devices you can have in 90 nanometer process also, or CMOS 65 also. So, even 1 volt you will get as you keep moving into the lower technologies. And so which means if I want to design a band gap which can operate at 1 and 1.2 volt, this circuit will not work, okay, because the output will be higher than that. So, that is why we require sub 1 volt band gap. Okay. Less than or so we know what we need. We need PTAT. Again, do the same exercise. You need PTAT, you need CTAT. Now, if I have a scaling factor here and then add the two, so what will be your VBG? K1 of VPTAT plus K2 of VCTAT. And if you choose K2, and we know VCTAT is VB, which is 0.7 volt approximately. Now, if K2 is less than 1, then you can scale down VB. Okay, so let us say you choose half. If you choose half, then so everything, the PTAT was added with 0.7 volt, now it will be added with 0.35 volt. So, obviously, this voltage will be much lower compared to 1.2 volt, and you can get the band gap voltage which is lower than 1 volt or below 1 volt band gap, which can operate at VDD less than 1.2 volt or so. The most important thing is choosing the K2. Then you choose K1 accordingly, because you want to match the slope. Now, the requirement of K2 will be determined by, K1 will be determined by the slope of your CTAT. So, you can design it for any voltage, accordingly you choose K1, K2. Okay, it is not that only one, because in the other case you had a VB which is fixed. So, your the K scaling factor will always be fixed depending upon your R1, R2 what you choose, M you choose, but that R1 by R2 multiplied by M factor will always be fixed, it will not change. But in this case, if you change the K2, then K1 requirement will also change. So, now you choose K1 and K2 based on what voltage you require. You can design it for 300 millivolt, 400, 500, any voltage you want, and that will define your K1, K2. Okay. So, we will look into that how we design this. So, you can design any value actually less than 1 volt. It is not that you will not get a fixed 1.2, just like a 1.2 fixed volt, you will not get a fixed 0.6. You can design it for 0.5 volt, 0.6, even 0.2 volt, 0.3 volt. It is up to you what is your output required here. Okay. So, we know that for sub 1 volt band gap you have to scale both delta VB and VB and add them up. So, what we need to do, we need to first convert into current. So, we need two currents. So, and if let us say I call this resistor as R3, so if you remember, this current was delta VB by R2 in standard band gap. Now, we need to have another current source which become VB by R1. Now, add them up together, this is your VDD. So, what will be this voltage? Plus delta VB by okay. I can also write it so what is delta VB? So, what is this term? Same as your standard band gap. Okay. And this is which means first you choose the ratio of R1 R2 to cancel the temperature coefficient, and then choose R3 over R1 ratio depending upon what value you require. Okay. So, which means R1 and R2 will define your, so R1 over R2 decides temperature coefficient and correct. So, once you cancel the temperature coefficient of VB and delta VB term, now then you can choose R3 based on what value you require, which means you can get any value. If I make R3 equal to R1, then you will get 1.2 volt around. If you make R3 over R2, or R1 is let us say 2x of R3, or R3 is half of your R1, then you will get roughly 0.6 volt. Okay. So, you can choose any. So, how do we do this? Let us see. So, how do we design it? So, delta V B by R we already did, we know how to do it. So, what you require? So, if this is V B 1, I will call it Q 1, Q 2. I want to make these two currents same. Okay. So, now your resistor is replaced with your MOSFET, and I talked about this yesterday. You can use either resistor or this current, and most of the time we use these current sources. So, now if this is 1x device and this is, let us say, mx device, this is your, what will be the sign of this?
Positive.
This is positive?
No, that is negative.
This should be negative, because there is one inversion in the PMOS. Okay. So, what is this current?
Delta VB by R. Delta VB by R.
By R2. How can I do VB by R? So, let us do another circuit. In fact, what you can do, let us call it Vx Vy. So, if I connect Vx here, I will get Vb. Why do I need another diode? You already have this, and you just connect it here, Vx minus plus now. If I remove the other diode R1, so what is this current now? The reason is then this current will flow again the diode, and there will be a mismatch. Okay. So, we will do that, but later we will combine the two circuits and make it one, but in a different way. Okay. So, this is, if this diode size is same, so you will also get VB1, same voltage here, correct? Now I have to add these two. So what should I do if I want to add these two currents? What shall I do? Yes. So put the mirror. So if this is W by L, W by L, W by L, so everything should be matched here. This is your R3. Okay. So you will get the same expression. Now let us see how we can combine these two and do everything using single op amp. Okay. So redesign. Using single op amp. Okay. So now we know we have a current delta VB by R2. We need to have one more current here, which is your, so output I want sum of two currents, which means this current now I have to make all these PMOS devices current. Instead of a single current, I want to make it two currents, which is basically delta VB by R2 and delta VB by R1. So this current is already delta VB by R2. What if I add this resistor and make it R1? So this voltage is already same as this VB1, correct? So this is VB1. So now the current which is flowing into this PMOS is delta VB by plus R. But what is the problem with this?
Current that side will also get changed.
Yes, so the current will change here. Huh? The currents are not same. So this device is, the Q2 device is seeing only delta VB by R2, because VB by R1 current is flowing into this resistor. But here it will see both the currents added up. So the currents are not matched. So what I can do? I can put the same resistor. Now they will be matched. Okay. So now both the devices will see the same current, and what you will see in the current mirrors, sum of the two currents. Now all I have to do, so this current is now plus VB by R1, and I will just stretch this. In fact, let us make it a bit cleaner. So this is W by L device. This is again W by L device, connector resistor R3, okay, and this will be your R3 by R1 into VB plus correct. So you can do it with a single op amp. So comparing to the standard band gap, do you see any drawback? here.
Sir, especially we can see the RDS effect, channel length modulation.
Mm-hmm. So what will happen due to that?
Due to channel length modulation, the current won't be exactly matched.
So which means the inaccuracy here might be more than compared to the standard band gap, because VBG, depending upon what VBG you choose. So this guy is the drain of other two PMOS which are directly connected to the diode side. So basically these two, this guy and this guy, they are seeing almost same VDS, because this is VB and other side is also VB due to negative feedback of this op amp. So what you see, VDD minus VB is the VDS. So let us say VB is roughly 0.7 volt and your VDD is 1.2 volt. So both will see 500 millivolt. Okay. Now if your VBG is not 0.7 volt, if you design this for 0.7 volt, then they will be roughly same. Okay. But that will also be at a one particular temperature, because VB is a function of temperature, but band gap voltage is not a function of temperature. So you might see some variation, maybe plus minus 100 millivolt or so, but due to obviously it will be much better compared to if you use a different value. Okay. So let us say you design it for 500 millivolt, then the VDS of this device will be much different compared to your VDS of the other two devices. Okay. So that is why inaccuracy here might be more compared to standard band gap. And other thing is, now you have to match these R1 also on both sides. So not only the current mirrors, but these resistors also have to be matched. So R1 R2 is the another thing, because we want to maintain the ratio, so they needs to be matched. Now we have a 2 R1 actually here, so they have to be perfectly matched. So any error between those two or mismatch between those resistors will also introduce error here. So more devices you add, there are more chances of inaccuracy, because if you require matched devices, now matching the more devices becomes harder compared to fewer devices. Still we get a very decent accuracy with this, and if you are much more concerned about this VDS mismatch, if you have a larger VDD, you can always use cascade. So with the cascade you can fix that, but without cascade obviously there will be some error due to that, which means you are forced to use these PMOS sizes, channel length much larger, so that you can reduce the effect of your channel length modulation.